Okay, this presentation is all about relative formula mass and simple mole calculations. There is another video that you can watch on more complicated mole calculations, but within this one we're just going to introduce it and keep it quite simple. What I'd like you to do for a starter is to explain the process of fractional distillation. So if you want to pause the video, take a couple of minutes, see what you can remember about fractional distillation, and then when you come back we'll have a look at that. Okay. So fractional distillation, we should remember, is a process of separation. It's used to separate a mixture that has substances with different boiling points. So if we look at the diagram, there we can see a simple fractionating column set up. So we've got a round bottom flask with our mixture of liquids in here, being heated by a Bunsen burner. A fractionating column here with a thermometer at the top, and then a condensing unit which runs down to a conical flask where we can collect our product. Now, for the purpose of examination, they can ask you quite a few things with this, sort of why is fractional distillation used, for example, or the process of it. So we have our mixture of liquids. Let's say we've got a liquid that boils at 50 degrees, 75 degrees and 100 degrees. So 3 liquids with different boiling points. So we get the Bunsen burner heating up, and the thermometer tells us when we've hit 50 degrees. So we control the Bunsen burner to keep this boiling at 50 degrees. And what happens is our liquid with a 50 degree boiling point boils, turns to vapor, travels up here, and then starts to cool as it's further away from the heat source. And as it starts to cool, it moves down this condenser until it collects in the conical flask. Once all of your 50 degree liquid boiling point has been collected, you replace the conical flask and you increase the temperature to 75. The thermometer records it. The 75 degree liquid boils, condenses, and then travels back down and is collected, finally leaving us with our 100 degree boiling point liquid in the round bottom flask. So we've been able to separate 3 liquids based on their different boiling points. Now, the important point with the condenser, which they like to ask in exams, you must label it if asked that the water goes in at the bottom and comes out at the top. Okay, you would lose credit if you did it the other way round. Similarly, if you are asked to draw in an exam or put a cross where the conical flask should be, it must be directly under where any collected liquid is coming out, not just here to the right of it or just here to the left of it or even under these water points here. It must be as shown on the diagram. Okay, so the presentation, we're going to look at how to carry out simple chemical mathematics, what we call quantitative chemistry. So for a grade 3, you've got to be able to recall what the mole and relative formula mass of a compound are, and I will touch on this later. There's not a spelling mistake here. I've not spelled mole wrong. That's just how it's used in chemistry. You'll probably see it in textbooks with the E missed off at the end. You've got to be able to describe how to calculate relative formula mass for a grade 4, and for a grade 5, there is a spelling mistake there. Obviously the word simple, obviously got carried away with chopping E's off the end of things, but can you explain how to carry out simple mole calculations in familiar and unfamiliar context? What we mean by unfamiliar context is if you have to change the subject to the formula. So we're familiar with the equation speed equals distance divided by time. A question might ask you to work out what time is given the other values. So that's unfamiliar because everybody remembers speed is distance over time, but can anybody remember what time is equal to? So when we say an unfamiliar context, you've basically got to rearrange to change the subject of the formula, and that increases the demand of the question, which is why it can be a grade 5 plus. Why do we need to know this? Well, the relative formula mass is a huge thing that you need to know. It's a key piece of quantitative chemistry. If you can do and understand relative formula mass and how to calculate it, then it can unlock so much more quantitative chemistry. It moves into mole calculations, simpler, more complex, titrations, which you can see in a separate video. In terms of a career, in terms of industry, again, any sort of career with chemistry would need to know how to calculate moles and how to calculate relative formula masses. I've just sort of highlighted the pharmaceutical industry, people who make drugs, so paracetamol, aspirin, that kind of thing. They're obviously dealing with very precise masses and volumes of chemicals, and if they get their quantity slightly wrong, then the end product could be a drug that doesn't work, or worse, it could be a drug that could kill someone. It could prove fatal. So it's all underpinned by this basic knowledge of formula mass and mole calculations. So if we take it back to something we looked at in a previous video that you should be familiar with, the mass number. And if we look at the periodic table, we know it's made up of all these tiles of elements, and it looks something like that. So we have the element name, in this case carbon, the symbol that's associated with it, in this case C, and then the bottom number 6, the top number 12. So just as a recap, we know that the bottom number is the proton or atomic number. It tells us it's got 6 protons. We know if it's got 6 positive protons that it must have 6 negative electrons. And finally, we know that it has 12 sort of subatomic particles with mass, what we call nucleons, because they're found in the nucleus, and we know it's got 12 of these, 6 of which are from protons, so the remaining 6 must be the neutrons. And the quick way to remember that is we do the 12, subtract the 6 to give us our neutrons. So that's the information we can get there. So we know that carbon's got 6 protons, 6 neutrons, and 6 electrons. Now we know though carbon very rarely exists just on its own, maybe in graphite or diamond, but other than that it exists in compounds. It's part of glucose, it's part of vitamin C, it's part of methane, you name it. Carbon is found in many things. Carbon dioxide is another example. So how do we look at a compound? Well, what we calculate here is something called the relative formula mass. Okay, and it's very simple. If we look at water, for example, H2O. Now the formula tells us quite a bit of information, but the key thing is how it's laid out. So if you look at this little number, the little number is always relating to anything to the left of the number. So we can see to the left of the 2 is an H for hydrogen. So basically this is telling me hydrogen 2. There are 2 atoms of hydrogen. The fact that there is no multiplier, no small number next to the oxygen, tells me that it is just this single solitary oxygen. So the formula H2O tells me hydrogen 2 and oxygen. So if we look at the periodic table, we can see that hydrogen's got a mass of 1 and oxygen has a mass of 16. So if we know the individual parts, we know that we've got 2 hydrogens, so it will be 2 times a mass of 1 plus the 16 for oxygen, which gives us a total of 18. So what about carbon dioxide? Well, again, with carbon dioxide, the carbon, no multiplier, so it's just this carbon on its own. Oxygen has a multiplier of 2, so we've got 2 oxygens. So again, we take our periodic table, we can see that the mass of a carbon is 12. We can see that the mass of an oxygen is 16, but we've got 2 oxygens, so that will be a mass of 32. So 32 for the oxygen plus the 12 of carbon gives us a total mass of 44. Okay, a couple of examples here. I'd like you to have a go at these. So you can see at the bottom A through to K. I'd like you to have a go at these. There's a couple more examples if you want to take time to have a look at those and see how they've come up with these answers. So CaCO3, a calcium, a carbon and 3 oxygens. The worked examples number 2 is important because we can see we've got these brackets here. That number 2 outside the bracket tells me that everything, remember we're looking to the left of the number, so it's everything to the left. But the brackets are saying, okay, it's just the bits inside the brackets. So we've got 1 calcium, because there's no number next to it, and then the brackets lump all of this together, the O and the H. So we've got 2 oxygens and 2 H's. That also becomes apparent if I look at this one here, H. We've got Mg brackets NO3 close brackets with a little number 2. So we look to the left of the little number 2, and that's everything in the bracket. So 2 times N and 2 times 3 oxygens, so 6 oxygens. The magnesium has no little number next to it. So again, there's just that 1 magnesium on its own. So what I'd like you to do is have a little go, read through those 2 further worked examples, make sure you understand what you are doing. So pause the video, have a look at those questions, give yourself about 10 minutes or so, and then when you're ready to go through them, we'll go through and have a look at what those answers are. Okay, so I'm just going to change that. Hopefully you found that not too difficult. Okay, so there you can see the answers populated in there. So I'm not going to go through them all individually. You can obviously mark your own, pause the video and mark your own questions. But if we just have a look at carbon monoxide, so we can see there, carbon has a mass of 12, oxygen is 16, 16 plus 12 is 28, magnesium oxide, 24 plus 16 is 40, H2O2, 2 for the H's, 32 for the oxygens is 34, and so on. I'm not going to go through them. Obviously, pause the video if you need to check your own answers. If you're not sure of any, try and work it backwards and see if you can end up with the answer. So if you didn't get 78, if you got, let's say you multiplied by 3 on the aluminiums as well, remember it's just one aluminium. So just check back and see if you can see where you went wrong. So now we know a little bit more about formula mass. It leads us in nicely to the mole. So that's the next progressive stage, if you like, the next thing that you need to know. Best way to describe a mole is a bit like how we use the word dozen to represent the number 12. Okay, we use the word mole to represent a number, so we wouldn't talk about, and I'll give you the number in a second, which you probably may be familiar with, but you know, when we're talking numbers for bakers, or you know, if we're talking about buying eggs or something like that, you'd say a dozen, not will you get me a box of 12, will you get me a dozen. So it's a word that we use to represent a quantity, a number. And that's because in chemistry we're dealing with very, very large or very, very small quantities. So we talk in terms of moles. And a mole of a substance contains this number here, 6.02 multiplied by 10 to the power of 23 atoms, molecules, or ions. And we call that number Avogadro's number. And there it is written out in full. So you can see it's quite a large number, but if we had 1 mole of a substance, that is how many atoms or molecules or ions. So if we had a mole of water, there will be this many water molecules. If we had sodium ions, it would have 1 mole would have this amount of sodium ions. Or if we had something made of carbon atoms, it would have this many carbon atoms in 1 mole. And as I've said earlier in the presentation, you'll notice in textbooks, instead of writing mole, it's often shortened to mol. And that's normal. Okay, so you'll see I've used it earlier in the presentation, and moving forward for the rest of this presentation we will be using the word mole with the E off the end. It's just to get you familiar with how it's used in exams and assessments and textbooks. Now we know that the formula mass, which we've looked at before, or if we're talking about the mass number for an element or compound, that represents 1 mole of that substance in grams. So if we're talking about a compound, we're talking about the formula mass, or for an element, we're talking about the mass number. So we saw on an earlier slide that the formula mass for water was 18H2O. So we know that 1 mole of water has a mass of 18 grams. So the general rule of thumb is if you work out the relative formula mass, stick a G on the end to convert it to an actual mass, so 18 grams, that is the mass of 1 mole of that substance. So if we had, I think it was carbon monoxide on the previous slide, carbon monoxide, CO, 12 and 16, 28. So 28 grams would be 1 mole of carbon monoxide. Carbon dioxide, 44, C and 2 O's, 32 plus 12 is 44. 44 grams is 1 mole of carbon dioxide. If we had 1 mole of carbon, okay, then carbon has a mass number of 12, so 1 mole of carbon would have a mass of 12 grams. And all of these, whenever we're looking at a mole of a substance, contain the same number of molecules, atoms, elements, ions, and that is Avogadro's number. So this 44 grams of carbon dioxide would contain 6.02 times 10 to the power of 23 molecules of carbon dioxide. Our 18 grams of water would contain 6.02 times 10 to the power of 23 molecules of water. And there's a mole equation, all right, that links formula mass, number of moles, and the mass in grams. And that equation is the number of moles of a substance is equal to the mass in grams of that substance divided by the relative formula mass of the substance. So if you find yourself in an assessment, in an exam, you will quite often be given the mass in grams of a substance. And my general rule of thumb is, if you're in an exam and you see a question where it tells you something in a question, John has 15 grams of carbon dioxide, if you do nothing else, work out the number of moles and you will get some credit. So even if you can't understand anything else in the question, wherever you see the amount of something in grams, you can work out the number of moles, because in your exam you get a free copy of the periodic table and you can work out using that the relative formula mass of whatever's mentioned in the question. So if a question has, John has 15 grams of carbon dioxide, work out the formula mass of carbon dioxide, 15 divided by that formula mass, and you've got the number of moles. You are going to get at least 1 mark on that question. So a question that you've looked at and gone, I don't get this, then at least you can pick up some marks. So for example, if we had 18 grams of water, we know the relative formula mass of water is 18, so we apply the equation 18 divided by 18, mass in grams divided by formula mass, and that tells us we've got 1 mole of water in 18 grams of water. If we had 500 grams of water, then we do 500 divided by 18, and that tells us in 500 grams of water, there are 27.7 moles of water. That's to 1 decimal place, rounded up. So it's a very simple equation to use, and it's one, as I say, that you can pick up quite a lot of marks in exams when you don't really understand the question. As long as you see a mass in grams, think, right, I'm going to work out the number of moles, you can't go far wrong. What I'd like you to do now. Again, I've given a worked example there, how many moles in 30 grams of carbon dioxide and how many moles in 175 grams of sodium carbonate. So you can see how that's worked through, working out the MR. This is the notation for relative formula mass. It's an M with a little subscripted R. So we know it's 44 for carbon dioxide, so we just do 30 divided by 44. Okay, so again, you might want to just pause the video if you need to rewind and check any of the notes and check any of the previous slides, just to make sure you understand how to do this. There are a number of questions, 7 questions at the bottom here, just using that equation, okay, looking at what you've got, so a C, 2 O's, a C and 4 H's, work out your formula mass and then do your mass in grams divided by that formula mass, applying that equation, and see how you get on. So pause the video, give yourself about 5 or 10 minutes, and then we'll go through these. Okay, so hopefully you have a chance to go through those. Again, I'm not going to go through them in any great sort of detail. I'll just pick a couple out. So here, 150 grams of methane, the relative formula mass of methane is 16. We've got a carbon at 12 plus 4 H's at 1 each, so 12 plus 4 is 16. 150 divided by 16 is 9.34. Again, I'm not going to take a long time on this. What I would suggest is if you want to just pause the video for a quick second now and check your answers and make sure you're happy with what you've got down, and obviously try and work back if you've got any wrong. The RFM here obviously stands for relative formula mass. Okay, so in terms of the mole equation, we've looked at it and we've seen number of moles is mass in grams divided by relative formula mass, but we can also rearrange the mole equation if we want to find the mass of a substance or the relative formula mass, as long as we have the other 2 values. So the other rearranged versions are given there. So mass in grams is the number of moles multiplied by the relative formula mass. So if we want to find the mass in grams and we're given the formula mass and the number of moles, or if we need to find the formula mass when we are provided with the mass in grams and the number of moles. So it's mass divided by moles. It's just a rearrangement, it's just changing the subject of that original formula. So what I'd like you to have a do is very quickly try and apply that and have a go at these ones. So there's nothing too taxing. I've given the first answer for you, so hopefully you can get to the answer of 355 grams. So these first ones, you're given the number of moles, and you can obviously use your periodic table to work out the relative formula mass. So again, give yourselves 5 or 10 minutes, pause the video, have a go at those and see how you get on. Okay, so there are the answers. I've just put them in red again and gone through them, so you can see for all of them I've got relative formula mass is 71. We know that we've got 5 moles from the question, so 5 times 71 is the 355 grams quoted in the question, so we can see that we've done it right. And all these are exactly the same. Trickier one is down here, D, because we can see NH4SO4, and we've got lots of NH4, so that's basically 2 N's and 8 hydrogens, because it's 2 times 4, and it's 4 oxygens, and the S is on its own, so 1S. So essentially 2 N's here, 8 H's, 1 S, and 4 O's. And when you work all that out, you've got a relative formula mass of 132. You multiply that by the number of moles from the top here, formula mass times that, and we get our 0.264 grams of ammonium sulfate. The last one is just using this equation. An experiment was carried out, blah, blah, blah. We are given the mass in grams and the number of moles. So we can see here the mass in grams and the number of moles. So we apply that and we find out that the relative formula mass of ascorbic acid, or vitamin C as it's better known, is 176. Okay. Hopefully you found that not too taxing. It's just a very simple equation, but as I say, the general rule is if you're not sure, if you're given in a question a mass in grams and a periodic table, you can work out the number of moles, which is going to open up some more marks for you. We get a little bit more complicated now, so I'm just going to talk about this idea of equations and moles. Now, if you go back and think about balancing an equation, we can't change the little numbers, those little multipliers that we've talked about in balancing, but we can put a big number in front of everything. If there's no number, then that's fine. But basically what those numbers are doing, they're actually telling us the number of moles. So we've been balancing equations for years, and we've never actually realised that that balancing number is working out the number of moles of a substance. So if we look at this equation, this is the equation for hydrogen gas reacting with oxygen gas to produce water. We can see that we need a 2 here to make that 4 hydrogens in total, 2 times 2. Here, 2 times 2 hydrogens gives us our 4 hydrogens, and 2 times 1 oxygen gives us our 2 oxygens, which balances here. So that's a nice balanced equation. What this basically tells me is, it's this. Here's one of our H2s, and here's our second H2, and here's our O2, and here's our 2 H2Os. And if we count those up, we can see 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens, 2 oxygens, and 2 oxygens. So it's balanced. We've got exactly the same on the left as we have on the right. So that's a balanced symbol equation. Now what that's telling me is that 2 moles of hydrogen gas need to react with 1 mole of oxygen gas to produce 2 moles of water. So basically it's a 2 to 1 to 2 ratio. We always need 2 hydrogen, 1 oxygen and 2 water for this reaction to happen. And that works the same on if we look at factors of these numbers. So for every mole of hydrogen, we need half as much oxygen. So if we had 10 moles of hydrogen, we'd only need 5 moles of oxygen, half as much. If we had 3 moles of hydrogen, we would need 1.5 moles of oxygen. So the factors are always the same. It is a ratio, 2 to 1 to 2. We always need half as much oxygen to produce the water. Okay, so as I said, 10 moles of hydrogen would react with 5 moles of oxygen to produce 10 moles of water. And that is important when you're trying to understand this. Those balancing numbers are a ratio of molecules. Okay, 2 molecules of hydrogen, 1 molecule of oxygen, 2 molecules of water. Your balancing numbers are key. But we might have something more complicated. So we might have 13.87 moles of hydrogen. So you might look at that and panic and think, well, I don't know, it's a 2 to 1 to 2 ratio. It's a very, very simple process. If you just look at these steps here, here's our hydrogen, oxygen and water from the previous slide with our 2 to 1 to 2 ratio. First thing I'm going to do is divide by 2, because I know if I've got 2 moles of hydrogen, dividing it by 2 to get it to 1 mole, I do the same with my oxygen and divide that by 2 to get 0.5 or a half. I then multiply it by 13.87 because I've got 13.87 moles of hydrogen, which gives me this number. If I multiply my 0.5 by the same number, because it's a ratio, then that gives me 6.94. And again, I can use that to work out moles of water going through the same process. I divide my 2 by 2 to get it to 1, and then I multiply it by 13.87. Okay, so it's just a way using those mole ratios of working out how many moles when I'm given a more complicated number. So like we said in the outcomes at the start, this idea of familiar and unfamiliar context, this is what is unfamiliar now, so it's bringing it up to a much higher level skill. Okay, we're coming towards the end now, but it is going to get a little bit complicated, so bear with it. If you need to pause at any point just to take it in and rewind and have another listen and have another read, that's fine. So just take as long as you need with this bit. So in terms of reacting masses, you could be asked to work out the mass of a reactant or product when you are provided with the mole data. So here's a typical question. Hydrogen and nitrogen react together to produce ammonia. How many grams of nitrogen would be needed to produce 16.3 grams of ammonia? Okay, so you might look at that and panic. First thing you're going to do is work out the balanced equation. Now, I'm not going to go through the whole process of balancing in it. You should know from the question that hydrogen and nitrogen exist as diatomic molecules. Remember Professor Hoberfinkel, all those elements, hydrogen, oxygen, bromine, and so on, that exist as diatomic molecules. And ammonia is NH3. You may be expected to remember that, or it may be given in the question in an exam. So it's worth remembering that ammonia is NH3. Then we balance it up. So we've got 6 hydrogens and 2 nitrogens on each side of the equation. So we can see it's a 3:1:2 ratio because of the balancing numbers. 3, 1, because if there's no number, it's telling us that there's one of those and a 2 there. So it's a 3:1:2 ratio. Then we use the mole equation. So as I said to you earlier, if you don't know how to do anything else, find something in grams, work it out. So we can see we've got 16.3 grams of ammonia. So mass in grams divided by formula mass, 16.3 divided by 17, because N is 14 plus 3 H's is 17. We know we've got 0.96 moles of ammonia. Even if you know nothing else, you've just got yourself at least 1 mark on your exam, because we can see in the question we are given the mass in grams. So just use that mass in grams to your advantage. We can then use the mole equation to see how much nitrogen we need. So we can see the ratio. If we forget about the hydrogen bit here, so forget about this 3, we can see it's a 2:1 ratio of ammonia to nitrogen. So for every 2 moles of nitrogen, of ammonia rather, we need 1 mole of hydrogen. Basically, nitrogen, we need half as much. Okay, so if we have 0.96 moles of ammonia, half of that is 0.48 moles of nitrogen. It's just the mole ratio. Now we've got 2 more pieces of information, because we know the number of moles of nitrogen. We've just worked it out. And using the free copy of the periodic table that you get in your exam, we can work out the number of moles of nitrogen. So we rearrange that equation and we solve it to work out the mass of nitrogen. So from a previous slide, you'll remember rearrange to find the mass in grams. It's the number of moles multiplied by the formula mass. The formula mass of nitrogen is 28 because it's N2, 2 lots of 14. So we know that the mass is the number of moles, 0.48, multiplied by the formula mass, 28, which tells us that the mass is 13.44 grams. So all we've done, from what looked quite a complicated question, we started with the basics. We can see this mass in grams. We were able to work out the number of moles of ammonia. Once we've worked out the number of moles of ammonia from the balanced equation, we were able to work out the number of moles of nitrogen. Once we knew the number of moles of nitrogen, and using the periodic table to get its formula mass, we could work out the mass in grams of nitrogen. You're talking about a 4-mark question in an exam there, give or take, depending on what else it might ask. Obviously, this isn't a full exam question, but you get the idea that just from that one piece of information and relative formula, so going right back, to what we said, why we're doing this, relative formula mass, mole calculations, fundamental skill, opening up so many other avenues for you. What I'd like you to do, you were shown how to calculate the mass of nitrogen from that last question. Hydrogen and nitrogen react together to produce ammonia. so on and so forth, I'd like you to apply the same principles now to try and find the mass of hydrogen. So we know that we had 16.3 grams of ammonia, and that told us, just quickly going back, that we needed 13.44 grams of nitrogen. How much hydrogen would we need? Now, there are two ways to approach it. There's a quick way, which is the obvious one, hopefully, and then there is the more long-winded way. The quick way we can only apply because we've worked out this. Okay, so I'm just going to give you a couple of minutes to have a think about it. So if you want to pause the video and see if you can work it out, how much hydrogen is needed. When you press play, we will go through the two ways. Okay, so just give yourselves a couple of minutes. Okay, the quick way then. So, there's a balanced equation, mass of hydrogen. The quick way, we know that the mass of reactants, everything on the left, must be equal to the mass of the products, everything on the right. So we know we've got the mass of hydrogen plus the mass of nitrogen equals the mass of ammonia. So if we change the subject to get mass of hydrogen on its own, if it's plus 13.44 on this side, we need to subtract it on this side, which tells us that the mass of hydrogen is 2.86 grams. That's the quick way. The quick way only works because we were able to work out the mass of nitrogen previously. So the quick way, that would be a 1 mark question. The long way assumes that we've not worked out the mass of nitrogen already. So the long way is basically what we did to work out the mass of nitrogen. So if we look, we knew we'd worked out the moles of ammonia, which was 0.96. So we knew that the moles of hydrogen from the mole ratio it's a 3. If we look here, it's a 3 hydrogens to 2 ammonia. So if we know ammonia is 0.96, we first of all divide it by 2. So we have 1 mole of ammonia, and then multiply that by 3. So we've got our 3 moles. And that gives us the answer of 1.44. So now we know the number of moles of hydrogen. We can substitute into that rearranged formula to work out the mass in grams. So we know it's 1.44 multiplied by the formula mass. Well, it's H2, so it's nice and simple. 1.44 times 2 gives us 2.88 grams. Now, hopefully, you've looked at that and you've gone, well, the quick way says 2.86 grams. The long way says 2.88 grams. So why mass is missing? Why is there some mass disappeared in one way compared to the other? Why is there 0.02 grams less the quick way compared to the long way? So I'll just give you a minute, have a think about that and see if you can understand why that mass might have disappeared. And it's a very, very, very simple reason. Okay, so a couple of minutes, have a think about that. Okay, there's nothing in terms of the chemistry side of things, it's a mathematical reason. And the reason the two masses are different, 2.86 and 2.88, comes down to maths, and it comes down to rounding. When we worked out very, very early on, a few slides back, looking at ammonia, I will have rounded up or rounded down. I will have done it. So if I just quickly rewind this back, it was here. If we look here, the 0.96 moles. If you do 16.33 divided by 17, I've given it to 2 decimal places. Okay. Now, actually, it comes out at 0.9 and then lots and lots of numbers that round to 0.96. So that 0.96 rounding obviously carries through when we do the 0.96 here, dividing it by 2 and multiplying by 3 to get to 1.44. It's not actually 1.44. The rounding changes it slightly, which is why we get a discrepancy, because the rounding up at that early stage gives us this. Now, my advice to you is in an exam, and I've done this purposefully, is so that you don't do the same. It was just to highlight why you get a different answer. In an exam, only round when you are giving the answer. So this earlier stage where I rounded to get my number of moles to be 0.96, when you do that, then don't put 0.96. Don't do the rounding. Write down whatever your calculator spits out and keep feeding that in, and only do your rounding when you get to the answer. And if the answer is requesting 2 significant figures, 3 significant figures, 2 decimal places, round it to what it is asking for. But that's just to show you why there's a discrepancy. Okay, so just in summary then, quite a lengthy one, but very, very useful. Some key skills in there, calculating relative formula masses and also calculating moles, the very simple mole calculations. The mole calculation there that we've just looked at, number of moles is formula mass, mass in grams, sorry, divided by formula mass. That can be applied to so many things. As I say, it comes in with so many skills that you'll see in other videos. So it is a fundamental, but it's very, very important that you can do that. So obviously take the time to have a look at this again if there's anything you're not sure of, but just making sure that you can calculate relative formula mass, taking the mass of the sum of the parts and working out what the formula mass is, and then using that equation. And if in doubt, if in a question you are given mass in grams, you have your free copy of the periodic table, so you can always use that to work out the number of moles. If nothing else, you would be picking up some marks. Okay, but making sure you can apply that in a number of contexts, and you'll see in subsequent videos where that's discussed. Okay, hopefully you found that useful, but if not, please get in touch with your teachers or have a look at the video again to make sure you understand it. Okay, thank you.